Hello, everyone. I am Matt DeLacluse, General Manager of RAECO Rents. I'd like to thank all of you for taking the time out of your busy schedules to join us for Health Effects and Control Technologies for Non-Ionizing Radiation. Our presenter today is Dr. Ramon Lopez, Assistant Research Professor at the Richard M. Fairbanks School of Public Health in the Department of Environmental Health Science. In this 45-minute webinar, he will cover the following: health effects from the exposure across the non-ionizing radiation spectrum, regulations and consensus standards regarding worker NIR exposure, identifying the areas of concern for worker exposure, methods of measuring NIR exposure, control measures to safeguard workers against NIR exposure, and then Ask the Expert will answer your questions at the end. Dr. Lopez is an assistant research professor at Indiana University's Fairbanks School of Public Health, where he teaches courses in environmental health and environmental calculations. From 2009 to 2014, he worked on a U.S. Air Force-funded project testing non-ionizing radiation technologies for performance and safety. Dr. Lopez is a certified industrial hygienist and serves as vice chair of the AIHA Non-Ionizing Radiation Committee Volunteer Group. He holds a bachelor's degree in applied mathematics from the University of Illinois at Urbana-Champaign, a master's of science in hazardous substances academic training and industrial hygiene from the University of Illinois Chicago, where he also completed his PhD in occupational safety. We welcome Dr. Lopez as a speaker. Thank him for sharing his time and expertise with the RAECO Rents customers. Because of the large number of attendees online, we'll be muting the phone lines. If you have any questions, there's a question chat tool built into GoToWebinar. Please enter your question, and we will go ahead and get them answered at the end. Now I would like to turn the microphone and presentation over to Dr. Lopez.
Well, thank you, everybody, for joining us on this presentation. As Matt mentioned, my name is Ramon Lopez. I am at the Indiana, the IU Fairbanks School of Public Health. It's an ugly day over here, so no one's in the office, which is great. But thank you for joining us on this webinar. An outline of what I hope to accomplish by the end of this webinar is: one, we'll go through the overview of what non-ionizing radiation is, so just a 10,000-foot level description of that. We'll review some of the health and biological effects for each category of non-ionizing radiation. Discuss how that health and biological effect data is related to some of the exposure standards or exposure regulations that are in place, and then also review some of the control mechanisms available sort of in a short overview as well. There's a lot of information in here, and I think there's a lot to talk about. So we're going to have to go through this somewhat quickly, unfortunately, because there is a lot of information in each category to sort of describe, right? So the 10,000-foot level of non-ionizing radiation, we talk about the basic model of the atom with a dense nucleus that contains the protons and the neutrons, and then you have the orbiting electrons, obviously, around that atom. The idea is that you somehow input energy into that atom, which causes that electron to absorb that energy and move to a higher orbital state. That electron wants to return back to its base state, so it releases that energy it absorbed in what we like to describe as a photon of energy that goes out into space, and that photon travels at the speed of light. That photon contains specific characteristics, basically an energy level, but also what we like to describe as a frequency or a wavelength. And the frequency and wavelength are inversely proportional to each other and related to that energy level of the photon as well. So we can describe that photon of energy in frequency and wavelength as well as in electron volts. In most of the exposure data that you can find, we talk about radiation. Let's see, move that to the next slide here. Come on, there we go. We talk about radiation in different terms. So in terms of non-ionizing radiation, the energy level is less than 12.4 electron volts. And within the non-ionizing radiation levels, we describe the extremely low frequencies and the radio frequencies in terms of frequency levels, right? So ELF is somewhere between 3 hertz and 3,000 hertz. In some of the literature, it goes from 1 to 3,000. And then the radio frequency begins at 3,000 and goes to 300 gigahertz, right? So we describe this in frequency. When we move farther down the spectrum into the infrared, the UV, and the visible, we describe these areas of the non-ionizing radiation spectrum in terms of wavelength. So 700 nanometers all the way to 1 millimeter being part of the spectrum, UV 100 to 400, visible 400 to 700. And once we get farther down that spectrum, we move into the ionizing radiation section, and that's described in photon energies for our presentation, greater than 12.4 electron volts. Okay, it's a little slow today. Let's see this. Okay, there we go. So that photon of energy that moves through space can be visualized in terms of a wave that's moving in a vector direction in a specific wavelength, as well. And in fact, if you look at the wave, it's actually 2 waves in one. So you have an electric wave, which in this case is moving up and down your screen, or a magnetic wave that's moving in and out of your screen itself. These 2 waves are orthogonal to each other. That's the electric wave to the magnetic wave, moving at a vector direction at the speed of light. So now we can look at the non-ionizing radiation spectrum, and we begin at the far left of the spectrum itself. So you notice we have the extremely low frequency range first, from 0 to 3,000 kilohertz, or between 3 and 3,000 kilohertz. Moving to the right, you have your radio frequencies, 3 kilohertz, 3,000 hertz, all the way to 300 gigahertz. And that comprises what we like to describe the electromagnetic field range of the electromagnetic spectrum. Farther over, we move into the optical field, where we have the infrared, the visible, as well as the ultraviolet. And we call this the optical range because they obey laws of optics, such as being able to be focused and refracted using mirrors, for example. Right? So you can see that as the wavelength begins to get smaller, the frequency increases dramatically, right? So higher frequency equals shorter wavelengths, and vice versa. Come on. Sorry about that. Looks like this is a little slow and moving from slide to slide for some reason. There we go. All right, so a few definitions that we need to talk about before we begin to talk about each one of the categories. The first idea is that of a static field, which is a constant field that does not change in intensity or direction over time. So it's going in the same direction, in the same loop constantly. And so the frequency of the static field is 0 hertz. So it's technically below the electromagnetic or the extremely low frequency range. And we describe these by DC currents, can be considered static fields. For the rest of the spectrum, we're talking about time varying fields. These reverse directions in regular intervals and can be described by alternating currents, AC currents, and these have frequencies greater than 0 hertz. Okay. All right. Next definition is talking about induced contact currents, especially at the lowest frequency levels. Touching up or brushing up against metallic objects can lead to a flow of current through the body. So that will be an issue that we're going to be discussing to a certain extent. Second on here is the induced current density, which is the electric current per unit area that's produced by the electric field. All right. So the most appropriate method of describing energy absorption in the body is the specific absorption rate. And this is what's used in a lot of the literature where research is performed in perfect conditions, right? In a laboratory setting where you can take measurements that you can't do out in the field. And the specific absorption rate accounts for the different densities of tissue and conductivity of tissue and how well these different tissues can absorb energy at different wavelengths. And so when it comes to the regulations or consensus standards that we describe, we begin to think of the body as a uniform piece of tissue, so that the specific absorption rate there only be one. But in reality, tissue absorbs energy at different wavelengths depending on the energy or the frequency of that energy, as well as how the individual is positioned compared to where the energy is coming from, right? Unfortunately, when we do field measurements, we can't calculate the specific absorption rate very easily. And so these SIR levels that are created using data in laboratory settings and other settings need to be converted so that they can equate a level that we can measure, right? And that's the electric field strength and the magnetic field strength. So in some of the data that we're going to be talking about, they'll describe specific absorption rate that then eventually is transferred into that electric field strength, if possible, or the magnetic field strength that are used in creating the regulations or the standards. Come on. Okay. If you look for non-ionizing radiation recommendations, there's a lot of different agencies that have some type of a non-ionizing radiation exposure standards or recommended standards. One of the locations that you can look for these are the International Commission on Non-Ionizing Radiation or Non-Ionizing Protection, called ICNIRP. They have a considerable amount of data and information available on the ELF and the radio frequency ranges for free online. So that's one of the best resources when you have a specific problem to deal with. The ICNIRP website is very helpful in that respect. But IEEE, ACGIH, NIOSH, and OSHA also contain information that's very helpful in making measurements for your specific situation and also making determinations on possible health effects from exposures themselves. ACGIH in particular is who we're going to be focusing on, or who I will be focusing on, because this is what most IHs seem to use and what we're most familiar with in that respect. But if you're looking for guidelines on general populations, ICNIRP is a great source for that. So most of the recommended exposure guidelines are based on thresholds of effect or thresholds of effect to very short-term health effects, right? So things that are noticeable almost immediately from coming in contact with the body. Some of them use primarily animal data to make their threshold recommendations. And so when that happens, usually there's some level of safety factor added to when health outcomes were observed in those animal models, in order to ensure that human populations aren't overexposed, right? So generally we use safety factors of either 2 for general for occupational settings, or 10, and for general population 4 or 15 is what normally has been used in the RF or the electromagnetic radiation region. As I mentioned, there's standards for occupations versus the general population. So usually for occupation, they're not as stringent as they are for the general population. Right? So we're talking about non-ionizing radiation today because there is a level of concern that's found. So it can cause unwanted injury to populations, and we know very little about some types of non-ionizing radiation, especially when we talk about long-term effects, which has led to a lot of unfounded fears, or what we like to describe as the dread effect, right? The idea that these radiative sources are causing specific health effects where there really isn't any sort of data available, right? And so our goal is to sort of come up with this data, even at times if we believe that it's very unlikely that things happen. And so I'll present a lot of that data here to give you an idea of what we know and understand and what we don't, right? So we'll begin at the far left of the electromagnetic spectrum at the extremely low frequency level. Somewhere between 0 and 3,000 hertz is the ELF section. The biological effects in this section are considered non-thermal, low induced currents more than anything else. General population exposures range between 5 to 50 volts per meter for the electric field, and somewhere between 0.01 and 0.02 microteslas for the magnetic field. The sources, the main sources for ELFs to the general population are power lines. In Europe, they use the 50 hertz frequency. Here in the US, it's a 60 hertz frequency. But it's also, ELFs are also prominent from almost any electronic device. So your video display terminal, your telephones, all produce some level of ELF and a level of exposure for the populations in the vicinity, right? Measurements of ELF are done using the electric field strength, which is described by the electric charge in volts per meter, or the magnetic field strength, which is the motion of electric charge, right? So what this means is you might be able to measure electric field strength even when there isn't movement of a current through a wire, but magnetic field strength only happens when there's motion of electric charge. And this is measured either in microteslas, which is the magnetic field or the magnetic flux density, or in amps per meter, which is the magnetic field strength. So these two values might be equal to each other in a vacuum, but they might differ somewhat in materials. So the what's been studied a lot and what we have very little information on is the cancer-causing outcomes of extremely low frequencies. The latest review that was done was in 2002 by the Agency for Research on Cancer, and they mentioned that electric field strength can be categorized as a Category 3 cancer-causing agent, which means there's very inadequate evidence that suggests that these fields are causing cancer. However, magnetic fields are categorized as 2B, which means they are possibly carcinogenic. So the data sort of shows that there is a likelihood of it being carcinogenic, but it isn't completely for sure that it is, right? And a lot of that, or part of the cancer-causing outcomes has been sort of pegged at the idea that magnetic fields disrupt the production or the release of melatonin by the brain. And melatonin is important because it is an antioxidant, so it reduces inflammation in the body, tumor inhibiting as well, and so it reduces the likelihood of cancer in individuals in populations, right? And so the theory that goes around when it comes to melatonin and ELF is that the extremely low frequency waves sort of trick the brain in thinking that those are light waves. And so it suppresses the release of melatonin by the body, and so increases the likelihood of some of these outcomes like cancer, depression, and suicide. There's been a considerable number of studies that have looked at this topic by studying ELF exposure for short-term periods in animals, as well as looking at human studies. And most of these are really not in agreement. So there's been studies that have shown that there is a decrease in melatonin levels from ELF exposure, and other studies that have shown that there isn't an increase in melatonin level from exposure. So it's not 100% sure. When it comes to occupations, one of the biggest studies that have been done on this topic is by Winjard in 2001, where they collected 138,000 electrical workers in a very large case control study that spanned a number of different countries. And they looked and they categorized these workers in terms of their likelihood of being exposed to ELFs on a regular basis, and studied to see what the outcomes were for those individuals. And what they found is that for workers that were in categories of jobs where ELF exposure was expected, they found an elevated risk of suicide that was connected to the number of years of performing jobs where there was high levels of ELF magnetic fields, right? And the author basically used that theory back about melatonin levels to explain part of the reasoning behind why these high suicide rates might be occurring in these populations. Another area of concern is with children exposures to ELF electromagnetic fields, specifically to the magnetic fields that in this area of study has been around for a couple of decades. There's been 3 large pooled analyses done in the last couple of decades. Greenland was one of the first ones, a second pooled analysis done also in 2000, and a third one done in around 2007, 2008. In this case, Greenland pulled together 12 case control studies that were done across the globe, and only chose studies that either estimated or measured exposure levels for children populations within the study itself. And what he found was, with the data pulled together, was that children that had regular exposures of greater than 0.3 microteslas had an odds ratio of 1.7 increase of developing leukemia when compared to the non-exposure group or the low exposure group of between 0 to 0.1 microteslas, right? Other reported biological effects where there's very weak evidence suggest things such as Alzheimer's disease, cardiovascular disorders, and reproductive dysfunction. So these generally come from epi studies with only maybe one study and very limited data available. So some indication that these could be occurring, but there's not a lot of data to confirm these outcomes. In terms of regulations and standards for ELFs, there's no federal standard that exists. The OSHA says that they cite the general duty clause. But ICNIRP in specific has looked at, done literature reviews on this topic to come up with recommended exposure guidelines. So the first thing they looked at was static magnetic fields, those that are less than 1 hertz in frequency. So 0 hertz would be a static magnetic field. 2 studies that they cited, the first one by Glover et al., exposed study participants to different levels of magnetic field. And what they found is that magnetic fields above 2 teslas cause nausea and vertigo in the populations, right? Van Europe very similarly looked at different magnetic field strengths and also found subtle changes in attention and concentration, as well as visuospatial orientation problems in populations above the 2 Tesla range. So the magnetic field strength above 2T was causing issues, and that would be the threshold of effect for human populations. Another short-term effect is the stimulation of muscles in the peripheral nerve from the flow of the electric current. And so studies have been done on this topic as well. And they've had individuals come in contact with the electromagnetic field. And what they notice is the most sensitive populations noticed the movement of the energy as low as 0.2 milliamps. They had pain on fingers in contact at around 0.9 milliamps and painful shock at about 8 milliamps, right? So we can use this information to create our regulatory standards. So the ACGIH-TLV for whole body exposure restrictions to time varying magnetic fields from 1 to 3,000 hertz is split into 2 areas of the frequency range. From 1 to 300 hertz, we have the magnetic flux. It's 60 divided by the frequency range. Above 300, from 300 to 3,000 hertz, the magnetic flux maximum allowable level is 0.2 millitesla. So it decreases as you go down to the left, right? For contact current restrictions for occupations between 1 hertz and 25 hertz, it's less than 1 milliamp. So in the previous slide, I showed you that at around 1 milliamp is when we start to have some pain from touching an object and the movement of current. And at higher frequencies, that restriction is relaxed some. For electric fields from 1 to 3,000, the restriction is not as severe as magnetic fields. So from 0 to 200 hertz, we're talking about less than 25,000 volts. And then from 220 to 3,000 hertz, it's frequency dependent, right? So the higher the frequency, the lower the allowable voltage restriction. When it comes to exposure restrictions to static electric fields, previously showed that individuals began to have effects of vertigo at around 2 teslas, and that's the allowable level for magnetic fields in workplaces for static electric fields, so from 0 to 1 hertz. All right. So for measuring the exposure, the methods are not necessarily well defined or available. One of the best resources that I found that are available out there is from NIOSH, that has an old document published in 1998 with a number of different methodologies that can be used in measuring extremely low frequencies. Some of the devices that are described are survey meters, low frequency meters, and then personal and area monitors for magnetic and electric fields as well. So methods of control on a regulatory level, there's been some movement in other countries especially to limit the amount of ELF exposure in populations. Specifically looking at the most sensitive population, so children. So things like reducing ELF exposures in play areas and common room areas has been instituted in countries like Italy, where at the 50 hertz range, they limit the exposures to 10 or 3 microteslas. Another a method that's been used is the redesign of appliances so that there's less of leakage of ELF from those appliances, and that's been a rule that's been put in place in countries like New Zealand and Sweden. Engineering controls increase shielding, so there's specific types of materials available that absorb ELF frequencies to a high degree that can be used in workplaces. Other methods of engineering controls include the redesign of electrical systems, so they reduce the unintentional ground currents that can flow through individuals. And then when it comes to transmission lines, it's the increased height of these lines, which has been instituted in many parts of this country. And I've noticed that in the Midwest, at least, where there's been a change in the height of these lines to much higher altitudes as before, or moving these lines underground altogether because the ground itself is able to absorb these energy levels very well, and exposure concentrations can be low in that respect. So second on here are the radio frequency ranges that go from 3,000 hertz up to 300 gigahertz. The biological effects being either thermal or high induced currents. The communication or the sources, is either communication from radar or television signals, from radio waves, and from induction heaters. Measurement of radio frequencies is done primarily with electric field strength and magnetic field strength. This is in the field. Once again, in magnetic field is measured either in microteslas or in amps per meter. We can then take that electric field strength or magnetic field strength to calculate the power density. And we use power density in the regulatory limits when we get far enough into the radio frequency range where heating of surface tissue becomes a problem. And so knowing how much energy is being absorbed per time per area of tissue is very important. And so we can calculate power density using the electric field strength or the magnetic field strength above a certain level of frequency. As I mentioned before, specific absorption rate is the ideal measure of absorption of energy in the body in watts per kilogram, but it's not a measure that we can easily collect in the field. But in certain situations, it might be the best method to deal with. So there's phantom models that can be used to measure specific absorption rate, especially very close to sources of radio frequencies. So the radio frequency range is the longest in the non-ionizing radiation spectrum, and so we subdivide this category into multiple sub-bands based on the technologies that are used in the creation of these radio frequencies and their uses as well. In addition, some literature breaks down the radio frequency ranges in terms of radio frequency and microwaves, but for this presentation, we'll be talking about this in terms of one very big range itself, right? So the Agency for Research on Cancer in 2011 reviewed cancer risk from radio frequency exposures and classified EM fields as Category 2B, specifically due to possible increased risks of brain cancers associated with wireless phone use, and these are generally in the HF frequency ranges. So there's some indication that it could cause or lead to an increased risk of cancer. However, other agencies have noted that this association isn't strong enough to cause any changes in the regulations or in the exposure standards that they have created. Effects on tissue are generally thermal in nature, and the frequencies themselves penetrate the body in decreased rates with increased frequency. So as you go from the far left to the far right, those radio frequencies penetrate tissue less and less and become pronounced on the surface of the tissue. And RF energy in general is absorbed well by water. So think about the difference between muscle and fat. So muscles contains greater concentrations of water as opposed to fat. So much better absorber of radio frequencies as opposed to fat. In terms of effects on reproductive and development, rat studies have been performed at different frequency ranges. And they found that it's likely that at very high specific absorption rates, where there's a lot of absorption of thermal energy, Male infertility can occur, and that's happened in some of these rat studies. There's also been teratogenic effects in rats noticed at high SAR exposure levels of 10 watts per kilogram. In humans, the threshold level is considered to be about 0.4 watts per kilogram, so much lower than the levels at which they're exposing these rat populations. But at these very high rates, they've noticed low birth weight, malformation of these populations, or stillbirths in these rat births as well. In terms of epi studies, there's possible links that have been noted between low birth weight of children from occupational populations that have been exposed for long terms to radio frequency ranges, low sperm count in male populations, and then differences in the sex ratios from exposure to RF. And that's been noted in at least one study done in Europe where working populations exposed to RF, male working populations exposed to RF, had children, female children at a higher rate than male children. In terms of ocular effects, cataract formation was reported in some animal studies, but other studies have found that these outcomes have not been noted, and so it's not something that we are clearly able to confirm. But it's also believed that at the levels of exposure that have been used in these studies, they were above what we considered safe for human populations, and so we believe that the current exposure standards are within safe limits for cataract formation. Other effects include synergistic effects that may occur when you have high exposure, high SAR level exposures and combined with chemicals such as coal tar, which can lead to increased likelihood of health effects in those situations. Behavioral effects have also been noted. In the US, 2 case control studies were the only 2 main studies that have been noted here in the US with high exposures to radio frequency. In both of these cases, they were in the military, exposure to waves that were produced from radars, and exposure times between 80 seconds to 5 minutes at very high SAR levels. These individuals had short-term effects of heating sensations in the chest and head, vertigo, as well as chest pain, but they also developed long-term effects such as insomnia, irritability, and hypertension that lends to the theory behind melatonin levels and exposure to radio frequencies. For these individuals in these cases, medical attention seemed to improve their outcomes and reduce their hypertension, irritability, and insomnia, but it's unclear what happened long-term past a few months from these exposures after the case control studies were published. Similarly, in rat populations, they've used behavioral changes as well as increases in temperature of the body to create the exposure standards for parts of the radio frequency ranges. In these cases, they looked at different animal models, including rats and monkeys, and specifically observed behavioral changes in these populations with different power densities and frequency level exposures. They looked at things like convulsions, endurance, work stoppage, aversion, and perception of these animals. And they noted that the specific absorption rate of 4.0 watts per kilogram is the threshold level for that health effect being observed in these populations, right? Because we use these rat populations, we then tag a safety factor of 10 for working environments. And so we say 0.4 watts per kilogram is an acceptable level of exposure to these waves. For general populations, we use a safety factor of 15, what we like to call uncontrolled environments, 0.08 watts per kilogram, which we believe is connected to an increase in body temperature and surface tissue of 1 degree Celsius. And that's when we probably or most likely begin to see behavioral effect changes in populations. And so these values have been converted to electric and magnetic field strengths in our exposure standards. So to note, regulations and standards between 3,000 hertz and 1 megahertz, induction currents interfere with the nervous system. So that's our main issue or health effect that we're interested in that range. Greater than 100 kilohertz, the EMF is absorbed and generates heat, mainly absorbed into the tissue and by organs. Greater than 10 gigahertz, the energy is absorbed well on the skin surface because of the amount of water, and so we're more concerned with absorption at the surface of the skin in those ranges. So once again, for regulations and standards, there's no enforceable standard that exists. OSHA has a recommended power density limit of 10 milliwatts per centimeter squared that's averaged over 6 minutes for frequencies between 10 megahertz and 100 gigahertz. So they're interested more in the surface heating component of the radio frequency range. So the density, the power density and exposure is averaged over 6 minutes. So you can have peak levels that exceed the MP as long as the average exposure over the course of any 6-minute period is less than a 10 milliwatt per centimeter square average that's noted by OSHA. ACGIH TLV has a more in-depth standard for radio frequencies. First, what they recommend is that you always measure the electric field strength near the vicinity of where individuals are working. If the frequency is less than 300 megahertz, then they also suggest that you measure magnetic field strength in amps per meter. If the frequency is also less than 100 megahertz, then we also need to consider the field strength limits and the induced contact current limits. And you can find these in the ACGIH TLV Table 1, Part B, right? So the lower the frequency, the more issues that you have to attend to, not only just the field strength, but also the contact and induced currents that might occur in those populations. So when we get farther to the right of the radio frequency range, the surface heating is a major problem, and we describe the exposure standards in terms of power density. And in these ranges, when you're greater than 100 megahertz, we can use the relationship that's noted here, where the power density is equal to the electric field squared divided by 377, or the power density is equal to 377 times the magnetic field strength squared. All right. So this is the table from the ACGIH TLV. So you can see that electrostimulation of nerves and muscle is the most prominent health problem that exists at the lower frequency range of radio frequencies. And so we have an electric field strength exposure standard and a magnetic field strength exposure standard. But when we move into tissue heating, we start to move into the power densities. And those are calculated using the electric field strength and the magnetic field strength that's plugged into the equations we just showed in the previous slide. Notice that the averaging time is 6 minutes, and these values are calculated with root mean squared values. So I'll show you what that means in the next couple of slides here. So an issue to contend with radio frequencies, especially at the low frequency range, is the difference between the near field and the far field, and what your measurements might mean in these different areas near the vicinity of the source. So if you're very close to the source itself, making electric field strength or magnetic field strength measurements might not be representative of what the actual exposure is. And so in these ranges, when you're very close to that, to the source itself, it's recommended that you use things like phantoms to make determinations of what the specific absorption rate actually is near this vicinity of the source itself. As you get farther away from the source, these electromagnetic waves begin to behave more as we described earlier in terms of an electric wave and a magnetic wave moving in a vector direction orthogonal to each other. And so making electric and magnetic measurements in the near field, maybe at least one wavelength away, might be an okay measurement, although they need to be multiple measurements performed in these areas to ensure that there isn't any change from one point in the space to the next. When you get farther, at least 2 wavelengths away from the source, these waves begin to behave more planar. They have a known temporal and spatial pattern that we can describe using that orthogonal relationship between the electric and magnetic fields. And so in this range, it's likely that you might only need to measure electric fields strength. So the standard is created in terms of root mean squared. And what that means is that you need to collect a spatial average of the radio frequency wherever the individual will be working, right? And the reason for that is that the exposure will not be uniform across the body of the individual. So there might be a lot more exposure, a lot more absorption of energy closer to the head as opposed to the legs. And so you need to collect a spatial average. A lot of the newer equipment today can do that automatically as you move vertically in a single from the ground up to about 2 meters. It can log it and create your spatial average. But if you have an older device, then you might have to collect multiple points along a vertical distance to actually collect your root mean squared average. In addition to that, especially if you're closer than 2 wavelengths to the source, taking area measurements or volume measurements might be better descriptor of what the exposure might be to the population. So just taking a vertical distance might not be enough, especially as you move closer to that source as well. Measurement techniques, electric and magnetic field measurements, tunable field strength meters, isotropic probes are the preferred instrumentation for the radio frequency ranges. Induced body currents can be measured with stand-on meters or clamp-on meters. Contact currents similarly using clamp-on meters. For radio frequency, engineering controls, shielding is a preferred method. For administrative controls, distance and time are also preferred methods, as well as appropriate signage. Something that we did a few years back in a lot of studies is looking at radio frequency protective clothing that either absorbs or keeps the electric energy out of the body altogether for protection of individuals. So that's another option that's available out there for working populations especially. All right. The third range is the infrared range. The spectrum ranges between 700 nanometers to 1 millimeter. The biological effect is generally called heating. The sources include sunlight, lamps, welding arcs, and lasers. However, we won't be talking about laser energy in this webinar, mainly because laser energy operates very differently than other types of non-ionizing radiation. There's 3 biologically significant bands along the infrared portion of the non-ionizing radiation spectrum. You have IRA, IRB, and IRC. You can see that IRC is absorbed well, or I'm sorry, absorbed highly by water. The IRA is absorbed best by tissue at very high efficiencies, and you can see that the absorption of water peaks in the IRB range, somewhere between 1,400 and 3,000 nanometers. In terms of skin, near infrared, between 700 and 1,400, absorption of the energy happens within the tissue, so it actually can penetrate deep into the tissue, and it's absorbed by the blood, by water, and by melanin. And so near infrared leads to burns on the skin, vasodilation of capillary beds, and changes in skin coloration. And this skin coloration change can be permanent as well. For far infrared radiation, the absorption happens mostly by water and bone, so it's closer to the surface of the skin and can lead to a thermal stress. For eyes, if you look at the infrared A level, 700 to 1,400, the energy level is transparent to the tissue in the eye, and so that energy can reach into the retina, especially when the aperture size or when the source size reaching the eye is very small. That source size can be focused onto the retina and can cause retinal burns, which is why we call this the retinal hazard region. So this is an area that we're very concerned with in terms of eye exposure. For the mid and infrared radiation, the energy is absorbed primarily by water at the surface of the eye. It can lead to cataract formation, especially in the mid-infrared range. So regulations and standards for infrared radiation, there's no federal enforceable standard that exists. ICNIRP has created exposure limits on this based on the source size, but also on the wavelength, energy, and the length of exposure. In this range, thermal injury of the skin and the eye are the dominant effects, but we need to note that there's an aversion response time for the eye of about 1/4 of a second. So as when you get closer to the visible range and you can actually see the radiation source, a standard that takes that into account is preferred, right? So you can quickly close your eyes and avert from the source. In terms of skin, the response is dependent on how quickly one feels heat. So especially farther to the right of the infrared range, where the energy is absorbed at the surface of the skin, less than 10 seconds or 10 seconds can be a long enough exposure time. The near infrared range can penetrate deeper into the skin, so the effect might not be as noticeable or as quickly noticeable or evident compared to the far infrared range. And in fact, and the IRC range is generally ignored because it's not a major source in most high-intensity broadband sources used in occupational settings. So the TLV is listed on here. So for skin exposure less than 3,000 nanometers, we set 10 seconds to be the exposure limit. And this is listed in radiant exposures. For the cornea and lens, we look at the levels between 780 nanometers and 1 millimeter. We differentiate between the exposure time of either 1,000 seconds, either more or less than 1,000 seconds, or greater than 1,000 seconds. 100 watts per meter squared is the allowable limit in that range as well. ACGIH TOV Table 2, you can find the exposure standard for retina between 700 and 1,400 nanometers. It's a very dense table, so that's why I didn't put it on here, but if that's of interest to you, you can find that in the ACGIH TOV book. Engineering controls, the best engineering controls are obviously the controlling of the emission at the source, erecting barriers such as glass that does not, or that absorbs the energy, steel or aluminum that might reflect the energy, and heat exchangers to keep the area cool. For personal protective equipment, welding filters, goggles, spectacles, and face shields are preferred. And in terms of clothing, lightweight cotton, aluminized aprons or coats that might reflect the energy, or ventilated suits might be appropriate. The final range in the non-ionizing radiation spectrum that we'll talk about is the UV range between 100 and 400 nanometers. The biological effect can be thermal or photochemical in this range. The sources include sun, the lamps, as well as welding activities. 3 biologically significant bands along the UV portion of the non-ionizing radiation spectrum: the UVA range, UVB, and UVC. UVC is a germicidal region, so we're most worried about this range, although it's the one that is produced or created where the sun doesn't have as much of an effect because it's absorbed well by the ozone. UVA is absorbed the least by ozone, and so it reaches the Earth at a much higher rate than UVC does. So we get mostly UVA and UVB from sunlight. Those 2 ranges are also absorbed well by melanin and hemoglobin, which is in your blood. And UVC is absorbed best by proteins, which means it's generally considered to be the most harmful range, but it's also very useful because it can kill a lot of bacteria and viruses. So in hospital settings where you're trying to disinfect areas, a lot of the times you'll be using UVC or germicidal light to deal with those sorts of issues in those environments. IARC reviewed cancer-causing UV radiation, and it found that UVA, UVB, and UVC are all cancer-causing agents, so they're group 1 carcinogens. So the data not only suggests, but they believe that this is true. In terms of epi-studies, these ranges of UV can cause a number of different types of cancers, mostly cancers of the skin, but we found that cancers of the lip from working outdoors, so occupational working activities, but basal cell carcinoma, cutaneous malignant melanoma, squamous cell carcinoma are also likely with high exposures of outdoor activities and from UVA, UVB, and UVC exposures. In terms of effects on the eye, UVB and UVC are absorbed in the cornea and the lens. They generally cause photochemical effects. So think about arc eye, that sandy feeling in your eye, also known as photoconjunctivitis. UVB exposure specifically leads to cataracts in your eyes because of the efficient absorption in the lens of the eye itself. UVC is absorbed well by water on the surface of the eye, and so we end up with sunburns to the eye itself. Effects on skin, generally considered sunburn, so photochemical outcomes, from exposure to UVB and UVC as well as UVA. There's also cases of photosensitization, so sort of an allergic reaction from being out in the sun from UVA and UVB radiation sources. In terms of regulation and standards and the data that's been used to come up with these, a number of studies have been performed. One that's listed on here is the irradiation of rabbit eyes with ultraviolet radiation. And what they did is they irradiated eyes using UV radiation between 290 and 320 nanometers, as well as 325 to 400 nanometers. And they noticed corneal damage at wavelengths less than 320 nanometers, with 300 nanometers being the most efficient. And the threshold of effect was occurred at about 0.15 joules per centimeter squared. And permanent effects, specifically cataracts or corneal damage, happened at twice the threshold level. In a separate study, they radiated both humans and rabbits to ultraviolet radiation in 10 nanometer wave bands to study photokeratitis. And they noticed that the action spectrum was between 210 and 320 nanometers, with the minimum threshold at 270 for both animals and humans. So, and that was occurring at about 0.005 joules per centimeter square, right? In terms of skin, the threshold for sunburn was between 250 and 304 nanometers, with the minimum threshold at 280 nanometers with 14 millijoules per centimeter squared exposure, and the maximum threshold at 296 with 47 millijoules per centimeter squared. At wavelengths greater than 300 nanometers, there was a requirement of increasing larger fluences of radiation to produce any sort of photochemical effect, right? So the threshold for sunburns was generally between 250 and 304. They could happen at higher wavelengths, but it required a considerable increase in the amount of energy being absorbed by the tissue. So the ACGIH exposure standards, this is a table with a 5 wavelength level. And so I just chose some of these just to show you where the exposure guidelines are. So if you look at UVA, we start at very high allowable exposures of 100 joules per centimeter squared at 400 nanometers, but it drops dramatically at close to the 300 level, where we start to see the lowest threshold of effects on population. So 1 joule per centimeter squared at 315, and even less, 500 millijoules or 0.5 joules per centimeter squared at 313 nanometers, right? As we get into the UVC, that allowable exposure continues to drop and reaches its lowest level at about 275 nanometers, where we see the greatest effect on skin as well as eyes, right? So 3.1 millijoules per centimeter squared. We can use those values in terms of figuring out the maximum allowable time in an area using the equations that are listed on here, as well as the table that's in the TLV. So for broadband sources, maximum exposure time can be calculated knowing the effective irradiance, which is listed on the same table as the TLVs. And for narrowband sources, you can use the equation that's listed on here, as well as the TLV, to find your maximum allowable time for UV radiation. Measurement tools for ultraviolet radiation are UV radiometers, as well as UV intensity meters. And control technologies for engineers, we're talking about isolation, enclosures with interlocks, shielding using opaque materials, so metal, wood, and cardboard, and polycarbonate plastics. For personal protective equipment, glass or plastic filters, things like face shields, safety goggles, long sleeve shirts, tight woven clothing, and for very low exposure level sunblock, although this is not as effective with very high exposure levels that might happen in occupational settings. All right, so references, and that completes this presentation. Any questions?
All right, that was great. Let me get to the questions here. Let's see. First one came up. Please ask Dr. Lopez if he is aware of any nonlinear health studies of NIR like the reported power and frequency windows of RF radiation.
Non-linear. I believe there is, where they try to make SAR measurements near the source. So the problem with being near the source is that the electric field and magnetic field strengths are not appropriate measures for determining the absorption of energy in that range. So we're more worried about the energy being absorbed in tissues. And so there has been studies done within that range, but as far as I understand, there isn't really a measure that can be used, or a standard that's available to say that if you're a specific distance very close to that source, that you're at a safe SAR level, if that makes any sense.
Okay. Somebody asked, for the Cuba and U.S. workers complaining of headaches and nausea without obvious signs of causation, it says theorized as possible low-frequency device. What are you feeling on that?
So I saw that study, or that article, and I didn't read too much into it. And I think that theory came up because a lot of the effects were very similar to what we described here for the ELF exposures. However, I think in the last couple of days, the theory has changed somewhat to possibly being a viral infection somehow. So I guess it's a possibility, but it'd be very difficult to prove that ELF exposure was the cause of those outcomes in those populations.
Okay. Have any studies been conducted on emission on NIR from cell phones, particularly involving melatonin suppression?
I mean, there's been a considerable number of cell phone studies, some long-term studies, longitudinal studies of at least 10 years of exposure that have recently been published. I don't know the exact outcomes of those, so it's something to look online for. But when it comes to melanoma, I think or melatonin possibly, I don't know of any melanoma studies with cell phone use.
Okay. Is Dr. Lopez aware of any non-thermal effects studies and exposure guidelines?
Well, there's exposure guidelines for current density to reduce the likelihood of electric shock from touching metal objects. And those were listed in the EMF section and the RF section. But in terms of exposure guidelines for long-term effects, there really aren't any. So we only have the guidelines basically for short-term effects, right? And as of today, the belief is that those are protective enough, at least, or that the data we do the best, basically. That's a threshold of effective where we know for sure that we're safeguarding workers and the general public.
Okay. Can you please explain how RF protective clothing works?
Sure. So I believe there's two different types of RF protective clothing. So some absorb energy, and some dissipate the energy by moving it through metal sheathing that's on the outside of the body, so that the electric field doesn't enter the body itself.
Okay. Is there any risk to firefighters using FLIR devices? IR cameras?
Well, that's a great question, and I really haven't looked into that. So I couldn't answer that question,
Okay.
honestly.
Fair enough. What is the mechanism behind the photochemical effects of UV radiation? Equivalent mechanisms in the other NIR ranges?
Can you repeat that question one more time?
What is the mechanism behind the photochemical effects of UV radiation? Question. And then equivalent mechanisms in the other NIR ranges.
So with the other NIR ranges, in theory, you might have photochemical effects, but thermal effects are dominant in that we feel the heat, and so we move away from the radiative sources, which is why we might not consider photochemical effects. In terms of the UV range, photochemical effects are dominant because the skin or the the energy is absorbed by other parts of the body as opposed to just the skin or the tissue, right? So the melanin within your hands or your arms, as well as blood, hemoglobin.
Okay. And then the last one, what are the most common technique errors you alert students to in measuring ELF and RF?
Well, so the how you hold the meter and the direction of the meter is very important, which is why we like to use antennas, three types of the multiple propagating antennas, because the direction in which you're holding it is very important. Also, taking averages over a space is very important. So a lot of the times just taking a single measurement is what people would prefer to use, but in reality you have to take either an area or volume measurement to get a real perspective of what the exposure might be for someone who's working in a space, right? Because most individuals don't stay standing in one area for a long period of time. They move around, and so their exposure might change depending on how close they are to the source and in which direction they're moving, etc.
Just to add to that, one of the instruments we have has fiber optic cables that you can attach to it so that the person studying is not standing right next to the machine. How important is that in testing?
It's an issue that's cited by IGNERP because an individual can shield the frequency and absorb some of the energy. And so you might end up with erroneous measurements if you have someone that's standing next to the devices or making measurements. So it might not be as accurate as it would be otherwise.
Okay, great. Well, that will conclude the questions. That's the last one we have. Dr. Lopez, thank you very much for your presentation. If anyone has any specific application questions that weren't answered here, please give me a call, 866-RENT-EHS or 866-736-8347. You can also reach me at matt@raecorents.com. If you want to know more about the technologies we supply, please follow us on social media. We put out a lot of good technical tips on my blog, blog.raecorents.com. You can follow us on LinkedIn and Twitter. We do record all these sessions, so they'll be up in the next couple days. You can find these on YouTube. If you have any topics you'd like us to discuss, please send me an email, and we will look into finding an expert for it. Watch the email announcements for upcoming webinars. Don't have anything scheduled yet for February, but we're working on it. All right, if at this point no further questions, we'll conclude the presentation. Thank you for attending, and thanks, Dr. Lopez.